Okay, in the beginning of Chapter 2, we begin to speak about describing graphs of functions, and there's going to be many ways that we're going to describe this. Some of them will be new, some of them will be from Algebra 2. Okay, the first thing we're going to talk about is where the function is increasing or decreasing. So I've drawn a line, so clearly the line is always increasing in the first box and always decreasing in the second box. This will not usually be the type of shape that we analyze. Generally, there'll be polynomials where you're going to have a lot of changes happening. So we look at the words here. We use the increasing and decreasing terminology to describe the y values. Okay, that's very, very important. So we're describing y values. Okay, that was a bad idea to do that. So let me just back up. Okay, so I'm going to, maybe I'll just circle it. So here are your y values that they're speaking about. So we're talking about the y values of the function increasing or decreasing as you analyze it from left to right. So when the function is increasing in the interval, like it is in this first box, we say that the function is continually increasing. So you should write, well, let's say continually rising. We'll use the word rising instead. So it's continually rising. Okay, then when the function is decreasing in the interval, then the function is continually falling. All right, so rising and falling, be certain of that terminology, and remember that you're speaking about what is happening to your y values as you move from left to right along the x-axis. So in the next page, we'll do the bottom of this first page of notes. Okay, number 2 talks about extreme points. Okay, an extreme point, or a relative extreme point, is a point where the function changes from increasing to decreasing or vice versa. So to be an extremum, an extreme point, you've got to have the following shape. It has to be either this shape for the function or this shape for a function to be considered an extremum. Okay, so it has to be a vertex. So vertex and extremum go hand in hand. So a relative extremum point of a function is a point at which the function changes from increasing to decreasing or vice versa. Another word for this is an, so we're going to put extremum right here. But know that we're talking about a vertex. Okay, a relative minimum point is where the function changes from, so let's see what's happening. The function is decreasing on this side and increasing on this side as you move from left to right. So a relative minimum, which is what we have here, here's our relative minimum, right at this point, is a point where the function changes from decreasing to increasing. A relative maximum is where the function changes from increasing to decreasing. So a relative maximum point is where the function changes from increasing to decreasing. Let's look for a second at the slope. So a relative minimum will have a negative slope, have a slope of 0 at the actual minimum point, and will have a positive slope beyond the minimum point. For it to be a maximum, it has to have a positive slope, a slope of 0 right here on the max, and then a slope that is negative beyond the maximum. So you can see this if you just draw, for example, on this function. If you were to draw a tangent line, you'll see the slope is positive. A tangent line here is negative. On the top, tangent line here will be negative. here will be positive. So you can either speak about it in terms of what is the slope, or whether the function is increasing and decreasing. In any event, you'll be able to identify relative maxes and relative mins in this regard. We're not talking about absolute yet. Absolute is going to be the highest value that the function can take on, whether it's an absolute minimum would be the lowest value the function can take on. Okay, I began to speak about absolute on the previous page, but let's clarify that a little bit more on this page. So the notes state the absolute maximum value of a function is the largest value that the function assumes on its domain. The absolute minimum value of the function is the smallest value that the function assumes on its domain. And I want you to note that not all functions will have a max or a minimum value. Functions with max or minimum values may not have absolute max or absolute minimum values. So let's look at these two figures, A and B, from figure 4. Since I have endpoints on figure 4A, I don't need to illustrate it anymore. But look at figure 4B. There is not an endpoint on the extreme right, so I'm going to put a little arrowhead right there so that you know your function is continuing beyond that point. Okay, so what do I have? I see that since my function has a positive slope here and a negative slope here, I have a max point at 2, 5. Since my slope is negative here and positive here, I have a min point at 4, 1. All right, so the max point, because of the nature of this function, is, and I'm going to change my color, okay, so this is going to be an absolute max point. And because of the nature of this function, 4, 1 will be an absolute min point. Okay, so I can analyze that using the terminology of the first derivatives, which is slope, or I can say that the function to the left of the maximum point was increasing. So I'll do that in pink. So the function to the left was increasing, so the y values were increasing. To the left, to the right of the maximum point, my y values are decreasing. Decreasing here, increasing here. So you can even talk about the slope being positive and negative, or the function increasing and decreasing. Moving on to figure 4b, because of that arrowhead, I know that my function can continue to increase. So even though I have, and I'll go back to black, even though I know I have right here a maximum point, it is a relative maximum point only. It is not an absolute because of this arrowhead. When I look at my min right here, I notice that that min, even though it's a minimum point, it is a relative minimum point because I have a lower point right here. So a little bit about absolute and relative. Every absolute max is a relative max as well, but not every relative max is an absolute max. So things to think about. Our next topic is going to be the changing slope, and this is an area of confusion for many. So we have to be exact in how we term slope changes. So we'll do that on the next page. Okay, when we look at slope, I can see in figure 6I that my slope is positive throughout the domain. I can see also in figure 6 double I that my slope is also positive throughout the domain. So let's look at this a little further. I know my function is always increasing. My function is always increasing. But is my slope always increasing? This is where you have to be very careful. So if I draw a series of tangent lines, what I see is that I have a flat slope initially, it's very steep here, and it's leveling off a little bit. So my slope is not always increasing. It's always positive, but it's not always increasing. Here, what do I see? Something very similar. Here it's flat. Okay, this is getting steeper, steeper, steeper yet. So in this figure, there are sections where the slope is always increasing, but you're always safer to say the function's increasing and the slope is positive, unless you look very closely. Places that you have slope always decreasing would be right here. The slope is negative, and it's becoming more and more negative, so therefore the slope is always decreasing. Okay, the function's decreasing, and this slope in this specific case is also always decreasing. Okay, here what's happening? I see if I draw little tangent lines, I see that my slope is always negative, but it's actually becoming less negative. So even though my function is decreasing, my slope is negative, but it's becoming less negative. So be careful on how you speak about slope. You really want to look very closely. Slope, as they say, is a slippery slope. You can easily make a mistake in speaking in generalities. Speaking in generalities should always be reserved to saying that a function is increasing or decreasing in y values. Don't speak about increasing or decreasing in slope unless you are very certain that you are correct. Okay, concavity is a very calculus-based concept when analyzing a function. So if you have a function, so let me undo that for a sec. Okay, if you have a function, and let's just say, for example, your function, I don't know, looks like this. If you try to draw a tangent line to it, and you find that you are drawing the line below so that you don't cross that curve, so that the function lies above the tangent line, then that function is concave up at that point. So we would say, since the function lies above the tangent line, where x is equal to a, then at x equals to a, the function's concave up. What does concave down look like? So let's say we have this function, and I'm going to draw a tangent line right here. I would draw the tangent line above, and I would say that that function is concave down because the function is below. So over here, there's a series of tangent lines drawn. The first one is a function that's concave up, and the second one is a function that's concave down. So if it's concave up, it kind of looks like a cup. If it's concave down, it looks like a frown. Okay, so a little simple way for you to remember that. When we start talking about second derivatives, I'll give you another way to remember this. Inflection points are another very calculus-based way to analyze a function. So we talked about concave up and concave down. Well, at an inflection point, and so we're going to say that these dots are inflection points, at an inflection point, the concavity is neither concave up or concave down because the concavity is changing there. So look at the concavity. I'll do that in green. So to the left of the first IP point, inflection point, I see that I am concave up. To the right, I am concave down. So the inflection point marks that change. For the second one, I'm concave up and then concave down. For the third one, I'm concave down and then concave up. But in all of these cases, at these inflection points, the concavity is changing. And we'll talk about how I can find those points in the next section. But for right now, what you need to know about inflection points is they are points. So therefore, an inflection point has to be denoted by an X and a Y value. Okay, it just can't be an X value because it's an inflection point. And it is a point where the concavity of the original function is changing. Okay, and we're going to use this figure to do a little analysis using the features of function analysis that we've discussed so far. So the first thing we're going to do is agree upon some of the points that are highlighted here. So there's 3 points. So the first point looks like 3, 5. That's pretty easy to read. Okay, the second point is 4, 4. And the third point, let's assume it's 5, 3.5. Okay, so those are the points that are already labeled in our figure 12. Okay, the first thing I'm going to do is I'm going to use a little color. Why don't we use red, and we're going to use red to identify where the function is increasing. So I can see that the function is increasing right here, and then the function is increasing again right here. So where is the function decreasing? So the function would be decreasing right in here. So if I'm going to analyze that, I will say, okay, my function is increasing from negative infinity up to 3 non-inclusive, because at 3 the function's neither increasing nor decreasing. And then it's going to also be increasing, so I'm going to put a little union sign there, from 5 to positive infinity. Again, I didn't include the 5 because at 5 the function is neither increasing nor decreasing. Okay, now how about if we want to say where is the function decreasing? So it was decreasing in that little window from the x value of just beyond the 3 to the y value that ends, or the x value that ends right before the 5. Okay, that's the interval on the domain, so I'm reading my x values, where the function's decreasing, where the y values are declining. Alright, so that's one type of analysis. What else can we talk about? Where is the maximum point? So I'm going to label that. We'll use, because we use light blue for that. So 3, 5 is a maximum point, and 5, 3.5 is a minimum point. Okay, now because my function does not have endpoints, the maximum is a relative maximum point, and the minimum is a relative minimum point. So what is the relative maximum value? So relative max value, I would just tell myself the y. So that's 5. It's a relative max value. What would be a relative min value? Again, when it's written like that, you're just going to tell me the y value. So a relative min value would be 3.5. All right, the last thing I want to talk about, well, I guess the last two things, are concavity and inflection point. So let's change our color again. So we're going to go with kind of like a, maybe we'll go with a dark green. Okay, so where is our function concave down? Our function's concave down from negative infinity all the way up to, but not including, the inflection point. Okay, then where is it concave up? So it will be concave up from the inflection point, or just a little beyond it really, all the way to positive infinity. So when I want to talk about the concavity, so this will be concavity, my function is concave, we'll do down first, concave down from negative infinity all the way to 4, non-inclusive, because at 4 the concavity changes. And then it's concave up from 4, not included, all the way to infinity. So if I have two types of concavity, I have one section that's concave down and one section that's concave up, I will have one inflection point. If I have no change in concavity, I have 0 inflection points. Okay, so the next thing we always want to identify is what is your inflection point. So our inflection point is the point 4, 4, and that's the point where the function is changing concavity. So when you talk about where your function is increasing and decreasing, that changes at the vertex. When you talk about concavity and where the function's concave up and concave down, that changes at the inflection point. When I talk about maximum point, I want an x and a y. When I talk about maximum value, I want only a y. Same thing for minimum point. Minimum point gives me both an x and a y. Minimum value gives me just a y. Inflection point will always give me an x and a y. So we're ready now to go to the next page. Okay, other features that we can analyze with functions that we certainly have done in Algebra 2. The y-intercept is defined as, what did we say, as where the function crosses the y-axis. So that's one thing you can say, but you can also say that it's where x equals 0. So draw a picture of it. Let's see. Okay, right here, that's going to be a y-intercept. How many y-intercepts can a function have? And the answer is 1. If your function looks like this and has 2 y-intercepts, it is not a function because it violates the vertical line test. All right? X-intercepts. So we talk about x-intercepts. We can say that an x-intercept is where the function crosses the x-axis. So that's one thing you can say. Or you can say where y equals 0. Okay, what is it also called? It's called the roots or the zeros of the function. Okay, when you draw a picture of one, so these points are x-intercepts. Do all functions have an x-intercept? And the answer is no. So a function like this would not have an x-intercept. Okay, functions can have as many x-intercepts as you want them to have. There is no violation. It does not violate the vertical line rule. if it has multiple x-intercepts. Okay, undefined points. I want you to think of that as the opposite of the domain. So when you look at this first function, y equals radical x, the domain would be that x has to be greater than or equal to 0. So where is this function undefined? So it's undefined where x is less than 0. All right, and that's how we're going to speak about undefined. So look at our next picture. So our next function that we see here, I see that it's a rational function. The first one was a radical function. So this is radical, this is rational. They both will result in undefined points. Okay, a rational function, what's the domain? The domain is that x can go from negative infinity, so I'm going to say domain, negative infinity up to 0, and then again from 0 to infinity. So that's the domain. So this function is undefined where x equals 0. Okay, so it's kind of the opposite of domain. So this answers the question, what points are undefined? Think about the opposite of domain. The last feature we're going to talk about is asymptotes, or are asymptotes, and we're going to do that next. Alright, so for asymptotes, there are two types. The first one that's discussed is the horizontal asymptote. It says graphs in applied problems sometimes straighten out and approach some straight line as x gets larger. Such a straight line is called an asymptote. Draw a function with a horizontal asymptote. So if this is my function, I can see that it's going to approach a horizontal asymptote, and let's just say that that's going to be where x is 3. So I'm going to have a horizontal asymptote where where y, let me backtrack that. So my horizontal asymptote is where y equals 3. So it has to be a y equals equation because it's a horizontal line. So remember, when we were talking about taking the limit as x goes to infinity, that was getting us a horizontal asymptote. So in this situation, I'm just lost my head here, this would be 3. Okay, in this situation, the limit as x goes to infinity is going to be 3. But that's not my horizontal asymptote. My horizontal asymptote is the line y equals 3. So make sure you understand what the question is so that you give the appropriate answer. If I ask you for the horizontal asymptote, you have to give me a line in the form of y equals. If I ask you for the limit as x goes to infinity, you have to just give me a value if such a value exists. So if either the limit as x goes to infinity or the limit as x goes to negative infinity exists, then that value will be the limit. And if you write it as a y equals, that will be your horizontal asymptote. Alright, so that's one asymptote. The other asymptote is the vertical asymptote. So how do I figure out a vertical asymptote? Well, let's look at a function. If f of x equaled, and I'm going to say this is x squared over x minus 2 times x plus 3, I can see that I'm going to have two vertical asymptotes. One will be at x equals 2, and one will be at x equals negative 3. So this function will not ever equal 2 or negative 3 because there'll be a vertical asymptote in place. So if you have These kind of features, you're going to identify them as part of a way of analyzing a function. So the next page, we're going to summarize everything that we just did. Okay, so here's a summary of the broad categories that we use for describing the graph of a function. So the ones that were new for us and that pertain to calculus specifically, I identified in red. So be able to identify intervals in which the function is increasing or decreasing, and the way that was different than Algebra 2 was that now we can talk about the slope of the functions being positive or negative. Identify relative maximum points. Okay, that's going to be a vertex. Identify relative minimum points. Again, it's a vertex. Coordinate pairs when I want a point. Y values when I just want a value. The maximum value, that's Y. Minimum value, that's Y. This is a function value and not a coordinate pair. Intervals in which the function is concave up, concave down, and the coordinate pairs of inflection points. Okay, those are all new topics. D, E, and F are things that we've discussed before, but all of these, A through F, will be important as we discuss functions.